Hello everyone, my name is Elliot Draper and I'm part of Speedworks training team, and today with Jonas we're going to present you how to accelerate. So why would you want to accelerate more and faster? In teams, for example, you're on a shoulder to shoulder challenge, you've got a through ball, you want to get away from a marking. Then if you can accelerate more and faster, it's a clear advantage you get on your opponent. For example, this was during the 2018 World Cup. Kylian Mbappe took the decision to accelerate a box-to-box run in the quarterfinals, gets a foul, penalty, and this is a goal for France in World Cup. I'm sure you all remember this goal from Gareth Bale in Champions League. Accelerate down the wing, smashes it, he scores 2 that day. But it's also important for defending to come back on the strikers, or even for goalkeepers. Manuel Neuer gets out of goal, wins a challenge. It's also important in rugby. This is Perry Baker, an American rugby player who scored the most tries for the Sevens. This is Anthony Watson, again, take the decision, accelerate. He's a Speedworks athlete, scores a try. Anthony Watson again, he's the one actually popping out, and again this ends up as a try. So yeah, speed is very important, and it definitely gives you an advantage on your opponent if you're faster than him. So today we're going to talk around in the first part what defines a good running model around velocity and acceleration. Then we're going to talk about how this is illustrated, what are the kinetics variables and kinematics variables that are associated with sprint performance. Then we're going to talk about reality, what happens in reality, what are the key variables and what are their role, and how to be effective while accelerating and running. And to finish the presentation, we're going to talk about how are the variables correlated, how do they interact with each other, and what would be our focus point to get faster. So good or bad run. A run is composed of 3 main phases: acceleration, speed maintenance at maximum velocity, and deceleration. A lot of researchers, especially JB Marin, showed that sprint performance is actually correlated with maximum velocity, but maximum velocity is a resultant of acceleration phase. As we can see, the top speed and top splits for world 100 meters records are all around 50 to 70 meters. So it means all what happens before 50 meters is acceleration. But acceleration can lead to different maximum velocities. As we can see, for example, these are several examples of runs that lead to a certain velocity, and the run that is the fastest, as we can see, this is there are several strategies to get to a certain velocity. These are several curves, velocity curves, that evolve over time and get to different top speeds. Actually, as we can see, this blue curve right here is actually one of the fastest at 10 meters, but less acceleration has been produced by that athlete. As a result, it actually ends up as the lower maximum velocity, while actually this other blue curve is the slowest at 10 meters and at 20 meters, but acceleration is produced and it gets to the 3rd top speed. So what will be our aim? Acceleration has to be as high as possible in the beginning, and then athletes have to try and limit its decrease as much as possible. Why? So as to have a velocity that is as high as possible, a maximum velocity. Now the question would be, how can we do this? Well, here comes the discussion of effectiveness and efficiency in sprinting. Effectiveness is about the degree to which something is successful in producing a desired result, and efficiency is a situation in which a person uses resources such as time, energy, space, etc. well, without wasting any. Effectiveness is about the goal, is about the outcome. So it's velocity, split times, and in team sport it will be getting to the ball before the opponent, catch back an opponent in a counter attack, or other actions during the game that involve speed. Efficiency is about the process, is about how do you get to your goal. If you manage to get to your goal by using more resources than you should, you are effective but not efficient. And if you use less than the resources you can use but you can't manage to get to your goal, you are efficient but not effective. Questioning now is what is efficient acceleration technique? Well, a lot of studies show that some kinetics variables are strongly correlated to sprint performance. The main one is horizontal force and horizontal power production. This is an illustration from a JB Marine study that illustrates the ratio of force RF, which is the ratio between horizontal force and total force. The more your RF is high, the more you produce horizontal force, or you get horizontal force from your total force production. You need to produce horizontal force at low velocities in the beginning of the run, so this is F0, and you need to produce horizontal force at high velocities, which is, let's say, over 8 meters per second, and this is V0. How can you do this? By producing a high ratio of force in the early stages of the run and then limit its decrease as much as possible. So have a DRF, a decrease in the ratio of force, which is as low as possible. This should ring a bell because we need to limit its DRF decrease as much as possible. Well, limit DRF, and so limit the decrease in ratio of force, such as we are looking to decrease as less as possible acceleration. So what are the kinematics in link with these kinetics? Well, produce force means being in contact with the ground, and produce it horizontally is orientate your body in the right direction. So as to be in contact with the ground as much as possible, you need to optimize the ground contact time and the air time and the ratio between both of them. And to produce it horizontally, you need to have low trunk angle in acceleration phase, so as a low shin angle. Velocity is distance over time. This means that we want to achieve more distance in less time, so have a higher step length and a higher step frequency, which is built around step time. Research has proven that in acceleration, the best individuals had higher step length, but the best trials within the individualities were the one with the higher step frequency. Acceleration is the change in velocity over time. So to have less decrease in deceleration, we want to achieve a more consistent raise in velocity and a more consistent step frequency. So this is a diagram from James Hay in 1983 that describes all the components around step length. So it is stance distance and flight distance that are also broken down in several components. It is all part of the puzzle, and by just changing a bit of the puzzle, such as touchdown distance, for example, or takeoff distance, or takeoff angle, we can change step length. Same for step rate, step frequency, which is composed of stance time and flight time. It shows that there's a lot of components that actually impact step rate and step length, and only changing a little component can change the step rate, and we can only have an action on a little variable and it will actually have an impact on a lot of other variables. So these are curves from Nagahara, a Nagahara study in 2014. It illustrates that to have an increasing velocity and as less decrease as possible in acceleration, we need consistent change, but also coordinated and effective change. For example, we're going to focus a lot during that presentation on drive index, which is the ratio between contact time and air time, and that gives an indication on the distribution of step frequency. So what about in reality? These are two ones from Reese Prescott, a Speedworks sub-10 athlete, that actually showed two different techniques of initial acceleration. So, what are the differences and how do they impact the run? Let's give you an overview side by side. Okay, so firstly, let's talk about step length and hip displacement. As we can see, run 1 in the black t-shirt has a higher and a longer step length, total step length, which is of 6.45 meters versus 5.88 meters. This is a 57 centimeters difference, and this difference is already there in the first step where there's already a 7 centimeters difference. However, hip displacement, even if it's still higher in the run 1 compared to the run 2, is more efficient in run 2 because the difference between run 1 and run 2 is only of 7% when it is of 9% in step length, total step length. This means step length is more efficient in run 2 because Reese is able to acquire more hip displacement from his step length, but it's still shorter. This can be explained by a shorter air time. Let's talk about air time. So step frequency, contact time, and air time. More horizontal force. It needs to produce more horizontal force. We need more horizontally oriented force vector, but also a higher drive index, which means spending more time on the ground than in the air. With these two videos, contact times are really similar, 0.95 seconds for both of the runs. This is a 0.4% difference, which is really small and non-significant difference. However, the difference in air time is significant. The difference is of 14%. Actually, in run 2, the total air time during these 5 steps is 14% less than in run 1. So, run 2 has higher drive index during initial acceleration. As we can see, the orange curve is actually higher than the blue curve, even if the first movement is lower. This means he spends the same amount of time on the ground but less time in the air. So it also means that run 2 has higher step frequency. As an average, it's a 4.1 Hertz for run 1 versus a 4.31 Hertz for run 2. So in run 2, Reese has higher drive index and higher step frequency, which means a better frequency and a better and a well distributed frequency. Now let's talk about body angle. The body angle in run 2 with the brown shirt is sharper. Shin angle and body angle is sharper throughout the run. Let's take that step for example. As we can see, the trunk angle in run 1 is 43 degrees and the shin angle is 46 degrees, when in run 2 it is 38 degrees and 37 degrees. So we have sharp angles, a more forward orientation, which means a more horizontal force vector, includes less time in the air, a higher ratio of force and less vertical displacement of the center of mass. Does it mean more horizontal force is produced? No, it means that a higher proportion of the total force produced is expressed horizontally. So let's come back to efficiency and effectiveness. We showed that run 2 had a better technique by a higher frequency, a more effective step length and a better orientation. So is it more effective? So it is more effective, sorry, but is it more efficient? Well, the step 4 average velocity, which is around 5.5 meters, was obtained by manual digitization, and in run 1 it is of around 7.3 meters per second, when in run 2 it is of 6.8 meters per second. But the time to 10 meters obtained with Lavrig speed radar is of 1.59 seconds for run 1 and 1.55 seconds for run 2. Efficiency depends on the task. At 5.5 meters, run 1 is more efficient, but at 10 meters, run 2 is more efficient. How can run 2 be less efficient at 5.5 meters but more at 10 meters? Well, good technique serves acceleration, and the more acceleration is produced, then the higher velocities you get to later in the run. I'm going to talk about how do the variables interact in real life example. A lower trunk angle to produce more acceleration. So we can see the athlete in the top video has sharper trunk angle through touchdown and toe off moments. The average angle in the top video is 41.4 degrees and in the bottom video it's 48.3 degrees. So the athlete in the top video orientates himself more forward. This results in slower first movement velocity here and here for the top run, which is of 2.87 meters per second for the top run versus 3.36 meters per second for the bottom run. But from step 3 to 4, the top run is actually faster than the bottom run. The average velocity is of 6.44 meters per second versus 6.06 meters per second as an average. So more acceleration has been produced by the athlete in the top run. However, the 5-meter times are similar, but the top run is slightly slower than the bottom run. Why? Well, lower trunk angle often involves longer ground contact times. We can see longer ground contact times from the athlete in the top video compared to the athlete in the bottom video. Actually, the total ground contact time is of 0.9 seconds for the top video, while it is of 0.79 seconds for the bottom video. This results in a longer step length and a longer hip displacement. Actually, total displacement for the athlete in the top video is of 6 meters 46, and in the bottom it's of 5 meters and 70 centimeters. But the air time remains similar throughout the run. As a result, the frequency of the athlete in the top run is lower, so he needs to develop a higher RFD so as to spend less time on the ground, or to switch faster so as to decrease his air time and so as to increase his step frequency. Another example, lower trunk angle to produce more acceleration. So we can see a lower trunk angle in the top video in the first 2 steps than in the bottom video. So yeah, this is 21 and 45 degrees versus 46 and 54 degrees. And in step 1 we can see angles of 40 degrees in the top run and 53 and 40 degrees in the bottom run. But from step 3 to 4, the trunk angle is actually higher. It's here of 55 and 49 versus 45 and 44. And in step 4 it's 49 and 55 versus 44 and 54. Also, we can see more shin roll during ground contact time in the top run. As an average of the shin roll, the athlete in the top run has a roll of 27.4 degrees versus a roll of 24.2 degrees as an average for the bottom run. So actually the orientation is better for the athlete in the bottom run. But the top run has faster velocity throughout the run. Actually, the average velocity through these first 5 steps is of 5.2 meters per second for the athlete in the top run, and it is of 4.8 meters per second in the bottom run. So, if orientation does not dictate velocity, how can we explain this? Well, a higher drive index to maximize force production. So just to remind you, drive index is the ratio between ground contact time and air time. It illustrates the distribution of step frequency. We can see in the top run a consistent raise in air time and a consistent decrease in ground contact time. In the bottom one, we can see a lot of inconsistency. For example, step 1 air time is 0.1 seconds and then 0.05, and then goes to 0.1 again, goes back down to 0.08 and then back to 0.1. So instead of a consistent increase, so as we can see in this first run, apart from block exit, then 0.7, 0.79, 0.79 and then 0.9, we see in the bottom a lot of inconsistency. We can also see in the top run a shorter total air time, which never gets over 0.1 seconds, and a longer average ground or average or total ground contact time. Which starts higher, it actually is higher through all the steps. As we can see here, the ground contact time is 0.16, 0.15, and then here it's 0.13, here it's still 0.15, and etc. Also, the athlete in the top run has efficient step length so as to optimize his force production. In the top run, there's less difference between hip displacement and step length. The average difference is actually of 2 centimeters. For the top run, it is of 11 centimeters for the bottom run. So the step length is more efficient, and the step length is used to create more hip displacement in the top run. As a result, the top run has a faster 5 meter time. As we can see here, the time to 5 meters is 0.99, when the 5 meters time here is nearly 1 second 0.1. So another example of how variables interact in real life is shin angle and shin roll during ground contact time. So shin angles at toe off and touchdown moments are indicators of orientation, good or bad orientation. They also give indication on the stiffness on the ground. We can see that in the top run there is more shin roll throughout each step. The average shin roll in the top run is of 23.5 degrees, while in the bottom run it is of only 18 degrees. This results in less acceleration produced, or even more, I would say, more deceleration produced. So the outcoming acceleration is less, and so this actually results in lower velocities. As we can see here, the velocity is lower, 2.6 versus 2.7 meters per second, and then here it's a bit higher, but then throughout the run it is lower. Here 4.8, 5.2, 6.1, 6.7, 7.0, 7.4. As a result, the top run has a slower 5 meter time, 0.98 seconds, and in the bottom rim 0.92 seconds. So a specific example of detrimental shin roll. I really want you to focus on that video on this right leg and its roll, its shin roll during ground contact time, and the change of angle in the shin. During this ground contact. Here, alright. So we can see in this step, the step 2, where actually the left foot is in contact with the ground, the shin roll is of 12.5 degrees. But in the third step, which is this one, the shin roll is actually of 32.3 degrees. But the air time of the two steps are identical, both of 0.07 seconds. Ground contact time is actually longer in step 3. It is of 0.138 seconds, while in step 3 it's 0.158 seconds. But this means there's a critical drop in step frequency and a raise in ground contact time, whereas we want the ground contact time to decrease rather than increase, specifically in this time in the run in initial acceleration. So we want to orientate forward and have as less shin roll as possible.